This podcast was created by Dr. Alyssa R. Jones for PSYC 5300 graduate level behavioral statistics using Notebook LM. The system was given specific parameters and restricted to content drawn from the assigned Crump Lab texts, answering questions with data and reproducible statistics for psychologists with R. The narration is produced using AI-generated voices. These voices do not represent recordings of Dr. Jones or the authors of the assigned materials. Although the podcast was generated from the designated course text, AI-produced summaries, explanations, and narration may still contain errors, omissions, or oversimplifications. Students should use each episode as a learning supplement and consult the assigned readings, course materials, and instructor guidance when clarification is needed.
So, what if I told you that you could take like a completely chaotic, totally unpredictable, just an entirely asymmetrical mess of human behavior, right?
Okay.
You put it into a mathematical blender, and every single time it pours out in the exact same, completely predictable, geometrically perfect shape.
I mean, honestly, that sounds like magical thinking.
Right.
Or at least some kind of gross oversimplification of how human beings actually operate in the real world. I mean, we're taught early on that biological and psychological systems are noisy.
Super noisy.
Exactly. They're sensitive to context and, highly resistant to being stuffed into neat little boxes.
Which is why the transition into graduate level psychology is such a brutal shock to the system.
Oh, absolutely.
Because you, the listener, you probably entered your program because you're fascinated by the messy stuff. You want to understand trauma or, cognitive linguistics, neuroplasticity, group dynamics.
Ton of stuff.
Yeah, the human mind. And yet here you are sitting in a windowless computer lab staring at a syllabus that basically implies the secret to the human condition is hidden inside a Greek letter.
The whiplash is just profound. You spend your whole undergrad career debating broad theories of human nature. And suddenly, in grad school, your entire ability to contribute to the field hinges on, variance, probability density functions, standard error.
It feels like a total bait and switch.
It really does.
There's actually a great quote from the source text by Charmaine J. Ford that captures the specific flavor of academic betrayal. She writes, "I have studied many languages, French, Spanish, and a little Italian, but no one told me that statistics was a foreign language."
Yeah, that linguistic analogy is, it's easily the most accurate way to frame this challenge. Statistics isn't just math problems.
No.
It's a syntax. It has its own vocabulary, these rigid grammatical rules, its own idioms, words you've used casually your entire life, words like significant or error or sample, power. They suddenly take on highly constrained, mathematically precise definitions.
Right. And if you don't become fluent in this new language, you literally can't read the literature in your field.
Which means you certainly cannot contribute to it.
Exactly. Which brings us to the actual mission of our deep dive today. We want to speak directly to you, the graduate student who is just trying to translate this foreign language into something you can actually use.
We need to set a tone of real patience today.
Yes, patience and rigorous clarity. Because we're tackling what is universally considered the most notoriously confusing hurdle in the entire quantitative curriculum.
Without a doubt.
And our goal is not to force you to memorize mathematical derivations or, formal proofs. Your textbook already does a fine job of making you suffer through those.
Yeah, we can skip the proofs.
Thank goodness.
Yeah.
Our mission is to build a rock-solid, intuitive understanding of the central limit theorem and sampling distributions.
This really is the critical threshold. Because if you don't have a deeply internalized intuition for these specific concepts, everything else you do in inferential statistics will feel like whinily pushing buttons in SPSS or R.
Just praying for a p-value less than 0.05.
Exactly. Just crossing your fingers without actually knowing what the software is doing underneath it all.
So here is our blueprint for this deep dive. First, we're going to define our terms to cut through the jargon. We're specifically focusing on 3 distinct types of distributions that textbooks just constantly blur together.
They really do.
Right. And second, we're going to run a mental simulation to watch the underlying math actually happen in real time. We'll basically build one of these abstract distributions from scratch.
I love a good simulation.
It's the best way to see it. And finally, we'll bridge the gap between abstract probability theory and the very real, very high-stakes world of psychological research. We're going to explore how this theorem is the only thing standing between scientific discovery and random noise.
That progression makes perfect sense. It moves us from the theoretical vocabulary to the mechanical application, and finally to the philosophical justification for why we run experiments in the first place.
Okay, let's dive straight into the vocabulary problem. If you open any advanced stats textbook, you are going to be assaulted by the word distribution.
It's everywhere.
Everywhere. But the text will casually jump between discussing a population distribution, a sample distribution, and a sampling distribution of a statistic, like all on the exact same page.
Yes, often without explicitly pausing to highlight that these are three entirely different universes of data.
Right. So let's clear the fog. Where does the confusion usually begin?
It usually starts with a population distribution, primarily because it's a phantom. It's a purely abstract theoretical construct. The population is the comprehensive set of all possible observations you want to draw conclusions about.
Okay, so if I'm a cognitive psychologist and I'm studying spatial reasoning in adults, my population is literally every single living adult on planet Earth.
All 8 billion of them.
Wow, okay.
Yes, and the population distribution is the theoretical mapping of all 8 billion of those spatial reasoning scores. It has true, absolute parameters.
And these are the Greek letters, right?
Exactly. We denote these absolute truths with Greek letters. So the true universe-level average of human spatial reasoning is mu. And the true variance, like how much those 8 billion scores deviate from the average, is captured by sigma.
But, and this is the cruel irony of scientific research, we will never, ever know mu or sigma. We don't have the funding, the time, or, the physical capability to test 8 billion people.
Of course not.
So the population distribution is this ultimate truth we want to discover, but it remains permanently invisible to us.
Which forces us to rely on the second type of distribution, the sample distribution.
Right. The stuff we can actually see.
Yes. If the population is the invisible theoretical truth, the sample is the concrete, flawed, finite reality sitting right there on your hard drive. It's a subset of the population.
Let's ground this with an example. We know IQ tests are explicitly engineered so that the population the invisible mu is exactly 100. And the standard deviation, sigma, is 15. The population distribution is forced into this perfectly smooth theoretical bell curve. But let's say I go to a local university and I convince 100 undergraduates to take this IQ test.
Okay.
That is my sample. And when I look at the data for those 100 specific people, their mean is 98.5.
And if you plot the distribution of your 100 participants on a histogram, the shape of your sample distribution is not going to be a perfectly smooth, perfectly symmetrical bell curve.
It's going to look messy.
Very messy. It will be jagged. It'll have gaps. It might lean slightly to the left. That discrepancy between your sample mean of 98.5 and the true population mean of 100, that is your sampling error.
The inescapable friction of empirical research.
Exactly. You didn't measure everyone, so your snapshot is inherently distorted by random chance.
I often think of this through, like, an ocean analogy. The population distribution is the entire Pacific Ocean. It has an exact, true global ratio of salt to water.
Okay, I like this.
But you obviously can't process the entire ocean. So you drop a single bucket over the side of a boat, you pull it up, and you measure the saltiness of the water inside. The saltiness of that one bucket is your sample statistic.
The ocean analogy is useful, yeah, but we should push it further to accurately reflect the complexity of a psychological population. Because the ocean is not uniformly salty.
Oh, true.
Right? There are localized currents, areas with higher evaporation, regions where freshwater rivers empty into the sea. If you drop your bucket near a river delta, your sample statistic is going to severely underestimate the true global salinity.
Wait, that implies my single bucket could be wildly unrepresentative just based on pure luck of where I dropped it?
Yes, it absolutely could.
And that variance between my single bucket and the global ocean is the sampling error.
It is that variance, yeah. And it's not just a theoretical annoyance. It is the core existential obstacle of all empirical science. How do we know if the bucket we pulled up is representative of the vast invisible ocean, or if we just happen to drop our bucket into some weird localized anomaly?
And this is precisely where the fog rolls in for most graduate students. Because to solve that exact problem, the textbook introduces the third distribution.
The dreaded third distribution.
Yes. And it uses a phrase that feels, honestly, deliberately designed to break your brain. The sampling distribution of the sample means...
It's a mouthful.
The moment you put the words sampling and sample right next to each other, the language center of the brain just shuts down. It's a grammatical nightmare.
The nomenclature is undeniably hostile to the learner, I'll give you that. But if we unpack the mechanics of what a sampling distribution actually is, we uncover one of the most elegant and powerful concepts in probability.
Okay, I'm listening.
It just requires a cognitive leap from thinking about individual data points to thinking about metadata.
Okay, let's trace that cognitive leap. Walk me through the mechanics of building this third distribution using the ocean and the buckets.
All right, so you drop your bucket once, you measured the salt and calculated a single mean. That gave you one sample statistic. Now imagine you empty that bucket back into the ocean. You drive your boat a mile down the coast, you drop the bucket again and take a second measurement. You write down a second sample mean.
So now I have two completely independent sample means drawn from the exact same population.
Now imagine you automate this process. You deploy a massive fleet of drones to drop 10,000 buckets randomly across the entire Pacific Ocean.
That's a lot of drones.
It is. And every drone measures the saltiness of its specific bucket and sends that single average back to your database. You now possess 10,000 different sample means.
Okay, I'm tracking this. I have a massive spreadsheet, but instead of each row representing one drop of water, each row represents the average of an entire bucket.
Exactly the right shift in perspective. Now take those 10,000 averages and plot them on a brand new histogram. That resulting shape is the sampling distribution of the sample mean.
Wow.
It is a distribution made entirely of statistics. The fundamental building block of this third distribution is not an individual person's IQ score or an individual drop of water.
The building block is a mean itself.
Exactly.
That is a massive paradigm shift because the first two distributions, the population and the sample, they're made of raw individual data points. But the sampling distribution is a meta-distribution. It's a distribution of distributions averages.
And its utility is profound. This meta-distribution allows us to visualize random chance. By looking at how those 10,000 bucket averages spread out, we can see exactly how much a sample mean is expected to bounce around naturally.
Just due to the chaotic luck of the draw.
Exactly.
Well, staring at definitions and meta-distributions conceptually is one thing, but to really cement this, we need to move away from the ocean and build one of these mathematical structures from scratch.
Yes, let's do it.
Let's run a mental simulation to see this underlying engine at work. And to make it a true stress test of the concept, let's start with an underlying population that is aggressively abnormal.
That's a vital parameter for the simulation.
Yeah.
If we start with a population that is already a bell curve, the magic of the sampling distribution is totally hidden. We need a population shape that is highly irregular or entirely flat.
So let's use the uniform distribution example from the source material, but let's map it to a psychological context. Imagine a study where participants are asked to rate their current stress level on a scale from 1 to 10.
Okay.
But imagine our target population is completely apathetic. They aren't even reading the question. They're just mashing buttons on the keyboard at random to get their participation credit.
A depressingly familiar scenario for anyone who has run studies with an undergrad participant pool, frankly.
Right. We've all been there. So every single number 1, 2, 3, all the way to 10 has an identical 10% chance of being selected.
Yes.
If we plot this true population distribution, it is not a bell curve. It has no hump in the middle. It's a perfectly flat horizontal plateau.
And because it's a perfectly flat, uniform distribution from 1 to 10, the true theoretical mean of this population, our invisible mu, is 5.5.
Okay, so our invisible truth is a flat line with an average of 5.5. Now, let's start our simulation. We recruit 20 of these button mashing students. This is our first sample. Non-dollar equals 20.
When you look at the data for these 20 students, you might see, 3 8s, a 2, a couple of 10s, a 4, and a 1.
It's just total noise.
Complete noise. You sum them up and divide by 20. Now, we theoretically expect the mean to be near 5.5, but for this specific sample, your calculated mean is 4.8.
Which makes complete sense. I got a 4.8 simply because, by pure luck, this specific group of 20 students happened to randomly hit slightly more low numbers than high numbers.
Yeah.
That 0.7 difference from the true mean is my sampling error in action.
Precisely. You write down 4.8, then you recruit another independent sample of 20 students. This time, the random key smashes skew slightly higher, and the mean of this second group is 6.1.
Okay, so I write that down too.
Yeah.
So my meta list of sample means currently has 2 entries, 4.8 and 6.1. Now let's inject some computational power into this. We write a script that simulates recruiting 20 random students, calculates their mean, records it, and repeats the process 10,000 times.
Now we're talking.
Right. We now have 10,000 separate sample means.
And here is the pivot point of the entire statistical universe. You take those 10,000 means, drawn from a completely flat horizontal population, and you plot them on a histogram.
And what happens?
The flat line is entirely gone. In its place, a perfectly symmetrical, smoothly sloping bell curve emerges, with its highest peak dead center at 5.5.
The flat population produced a bell curve of means. That is, I mean, it's completely counterintuitive at first glance. Why does the shape fundamentally change like that?
It is entirely driven by the ironclad laws of combinatorics and probability. Consider what it would take for one of your samples of 20 students to produce a mean of 1.
Well, to get an average of 1, every single one of those 20 students would have to randomly press the number 1.
Exactly. The probability of a 10-sided random variable landing on a 120 consecutive times is astronomically low.
It's practically 0?
It is practically 0. And the same combinatorial barrier exists for getting a sample mean of 10. Every single student would have to press 10. Therefore, the extreme tails of our new sampling distribution are incredibly thin. Almost none of our 10,000 samples will yield an average of 1 or 10.
Oh, I see. But the middle is a completely different story. To get a sample mean of around 5.5, I don't need 20 identical numbers.
No, not at all.
I just need a messy mixture. I need like a couple of 2s offset by some 9s, a 3 balanced by an 8, and a handful of 5s and 6s.
Exactly. There are literally millions of different combinations of raw scores that'll average out to roughly 5.5.
Wow.
Because there are exponentially more pathways to arrive at a mixed bag of high and low numbers than there are pathways to arrive at a homogeneous extreme, the vast majority of your 10,000 sample means will naturally congregate in the middle.
The highs cancel out the lows.
Yes, they pull the average relentlessly toward the true center. Thus, the bell curve is constructed by the sheer weight of probability.
The simulation is just mesmerizing because it isn't just a quirky trick with a random number generator. It's a visual proof of a fundamental property of nature.
It truly is.
And that mathematical reality is codified in what we call the central limit theorem.
Right. The central limit theorem, or CLT, is the bedrock upon which all of parametric statistics is built.
It's the big one.
In its most distilled form, it states that as your sample size increases, the sampling distribution of the mean will approach a normal distribution, a bell curve, regardless of the shape of the underlying population distribution.
I want to aggressively underline that final clause, regardless of the shape of the underlying population.
It's the most important part.
The uniform flat line is weird, but we can imagine stranger populations. What if our target population is highly skewed, like an exponential distribution?
Reaction times in cognitive psychology are a classic example of this severe skew.
Okay, how so?
Well, if you ask participants to press a button as soon as they see a green light, most human beings will respond very rapidly, hovering around, say, 200 to 300 milliseconds.
That makes sense.
This creates a massive spike, a dense mountain of data, on the far left side of your distribution.
But inevitably, a few participants zone out, they check their phone, or they sneeze, and their reaction time stretches out to 2,000 or 3,000 milliseconds.
And those inattentive participants create a long, thin, asymmetrical tail dragging far out to the right. The population distribution looks like a steep playground slide.
Right, totally lopsided.
Exactly. It lacks any of the symmetry required to be a normal curve.
So if our invisible truth is a steep playground slide, what happens when we start deploying our buckets? Like when we start sampling?
This is where the sample size, nuller, becomes the critical variable. If you only sample 2 people at a time, so $1 equals 2, your sampling distribution of means will still look distorted.
It'll still look a bit like a slide.
Yes, it will carry some of that heavy skew from the population.
Mm.
But as you increase the size of your sample...
Let's say we crank nullers up to 50 reaction times per sample.
Perfect. When $$ reaches 50, the central limit theorem fully asserts itself. Even though the underlying reaction times are violently skewed to the right, the distribution of the averages of those 50-person samples will form a perfectly symmetrical, unskewed, beautiful bell curve.
The mathematical blender doesn't care what shape the ingredients were when they went in.
Not at all.
If the sample size is large enough, it always pours out a bell curve.
Always.
This feels like an appropriate time to unpack the concept of the standard error because while the CLT guarantees the shape will be a bell curve, the sample size dictates exactly how fat or thin that bell curve is going to be.
That's a crucial distinction. The standard error is simply the standard deviation of our sampling distribution. It measures how much our sample means naturally spread out around the true population mean.
And this is a classic trap for graduate students. You have the standard deviation of the raw sample, and you have the standard error of the mean.
The terminology overlaps again, which causes endless grief. The standard deviation describes the dispersion of individual raw scores like how much one participant's reaction time differs from another's. The standard error describes the dispersion of the means, how much one 50-person sample average differs from another 50-person sample average.
Right, and mathematically, the standard error is calculated by taking the population's standard deviation and dividing it by the square root of your sample size, $1. Because no dollars in the denominator, the relationship is inversely proportional.
Which means as your sample size grows larger, your standard error shrinks.
Let's visualize this geometrically. If we go back to our 1 to 10 button mashing simulation, when none dollars was 20, our means clustered around 5.5, but they still had some wiggle room.
Yeah, quite a bit of wiggle room.
They might routinely bounce between 4.5 and 6.5. It's a bell curve, but it's a somewhat wide, forgiving bell curve.
But if you decide to recruit a massive sample, say, equals $1,000 participants per sample, the geometry fundamentally transforms. Well, when you average 1,000 random numbers, it is functionally impossible for that average to drift very far from the true center of 5.5. The thousands of high and low random button presses will aggressively and efficiently cancel each other out.
So the variance vanishes. The sample means won't bounce between 4.5 and 6.5 anymore. They'll be packed incredibly tightly, maybe only oscillating between 5.4 and 5.6.
Exactly.
The bell curve goes from looking like a gentle hill to looking like a hypodermic needle.
A needle pointing directly at the truth of the population parameter.
Yeah.
The larger the sample, the smaller the standard error, and the more faithfully and tightly your sample statistic maps to the invisible reality.
This mathematical inevitability brings us to a fantastic historical quote from the source material. Jacob Bernoulli, one of the brilliant and apparently quite arrogant founders of probability theory, wrote about this phenomena back in 1713.
Ah, yes. Bernoulli.
He said, "Even the most stupid of men, by some instinct of nature, by himself and without any instruction," which is a remarkable thing, "is convinced that the more observations have been made, the less danger there is of wandering from one's goal."
Bernoulli's phrasing is aggressively elitist, obviously,
Very 1713 of him.
but he is isolating a deep pre-mathematical human intuition. We inherently trust volume. We understand instinctively that a larger aggregate of evidence yields a more stable reality.
Like if I hand you a coin and you flip it twice and it comes up heads both times, you don't immediately call a press conference to announce you've discovered a coin that defies physics. 2 flips is a tiny sample.
The variance is expected to be high.
Right.
But if you flip that same coin 10,000 times and it comes up heads 10,000 times, your intuition shifts from this is random noise to this is a systemic manipulation.
Right.
The central limit theorem and the calculation of standard error simply provide the rigorous mathematical scaffolding that proves our mammalian intuition is absolutely correct.
Which provides the perfect bridge into the final and honestly most vital phase of our deep dive.
Yes, the so what?
Exactly. We've built the meta-distribution. We have marveled at the mathematical elegance of the central limit theorem. But we have to connect this to the real-world reality of psychological research.
We really do.
You, the listener, need to know why this theoretical machinery is the only thing that justifies your ability to publish a paper or complete your dissertation.
We must transition from probability theory to statistical inference. This is where we use the known behavior of random variables to test hypotheses about human interventions.
So let's put you in the lab. You're running a clinical trial. You want to know if a specific intervention, we'll call it variable X, causes a measurable change in a psychological state, variable Y.
Okay, set the scene.
Let's say you've designed a new intensive mindfulness protocol, and you want to prove that it significantly reduces generalized anxiety scores.
Well, to prove that your mindfulness protocol actually works, you must first do battle with the null hypothesis.
The dreaded null hypothesis.
The null hypothesis is the deeply pessimistic, highly conservative assumption that your intervention variable X is completely useless. It assumes the mindfulness protocol does absolutely nothing to alter anxiety.
It really is the ultimate scientific buzzkill. You spend 2 years designing a protocol, and the math forces you to start with the premise that you basically wasted your time.
It feels harsh, but it is scientifically necessary because it provides us with a baseline of random chance.
Right.
If the null hypothesis is true and your therapy does nothing, then your sample of 50 patients who went through the protocol is functionally identical to a random sample drawn from the untreated, highly anxious population.
And this is exactly where the central limit theorem swoops in to save the day, because we know exactly how random samples behave.
Precisely.
Hmm.
Even if the population of anxiety scores is a chaotic, skewed mess, the central limit theorem guarantees that the distribution of sample means 4 groups of 50 people will form a perfectly predictable, symmetrical bell curve centered on the population average.
So we can mathematically construct a map of where a sample mean of 50 people should land, simply based on the natural bounce of sampling error.
Yes.
We know exactly how wide that bell curve is thanks to the standard error. We have defined the strict boundaries of random chance.
You have constructed the null distribution. Now, you look at your actual empirical data. You calculate the mean anxiety score for the 50 patients who actually completed your mindfulness protocol.
And if that sample mean lands right smack in the middle of our predictable null bell curve, well, it's devastating.
It is a non-significant result.
Yeah.
You have to intellectually concede this level of anxiety is entirely consistent with the natural variance of an untreated sample.
The therapy didn't do anything special.
Right. The therapy did not exert a measurable force beyond random chance.
But what if it doesn't land in the middle? What if the mean anxiety score of my treated patients is incredibly low? Like, what if that sample mean land way, way out on the extreme left tail, miles away from the center of that predictable bell curve?
That is the moment of statistical significance.
Yes.
The central limit theorem allows you to calculate the exact probability of your sample mean occurring if the null hypothesis were true. If your mean lands so far out on the tail that the probability of it happening by random chance is incredibly tiny, say less than 5%.
The infamous p less than 0.05.
Yes. If the probability is that low, you have mathematical justification to reject the null hypothesis.
You can actually make a claim.
You can state with quantifiable confidence the odds of getting a sample this unanxious from the untreated population purely by accident are astronomically low. Therefore, it is highly probable that this sample does not belong to the untreated population anymore. Variable X, the mindfulness protocol, exerted a systemic force. It caused a change.
This is the profound revelation that makes the whole semester of struggling with Greek letters worth it. We use the theoretical sampling distribution to draw a hard boundary around luck.
Exactly.
We map out exactly what luck looks like so that when we see something that defies those boundaries, we can boldly claim we've discovered an actual effect.
It is the epistemology of modern science. We cannot prove absolute truth, but we can rigorously quantify our uncertainty.
But, a skeptical grad student might push back here and say, why go through all this theoretical gymnastics with bell curves and standard errors? If you want to know if the therapy works, why not just run the experiment 1,000 times? Or, better yet, just give the therapy to the entire population of anxious people?
The answer lies in the harsh constraints of reality. The economist John Maynard Keynes is quoted in the source text with one of the most pragmatic observations in scientific history.
Oh, I love this quote.
In the long run, we are all dead.
It is grim, but it perfectly encapsulates the problem.
A long-run statistical guarantee, the idea that if we take an infinite number of samples, we will eventually uncover the exact, infallible parameter of the universe, is philosophically interesting, but practically useless to a researcher who needs to publish a paper this decade.
Seriously, we do not have the grant money to test 50,000 people. We don't have the lifespan to run 1,000 iterative clinical trials.
We only have the time, the energy, and the budget to recruit one single sample of 50 people. That is our reality.
And the central limit theorem is the mechanism that allows us to cheat time and resources. It allows us to take that single isolated sample, place it against the theoretical backdrop of the sampling distribution, and extract profound generalizable meaning from it.
It's a bridge. It bridges the gap between the finite data we can afford to collect and the infinite population we wish to understand.
I really want to take a moment to offer some serious reassurance to you, the listener. If you have been feeling overwhelmed by populations, samples, variances, and exponential playground slides, take a breath.
Yeah, take a deep breath.
The reason we have taken this extensive, deeply conceptual journey is because the central limit theorem is the hidden engine under the hood of literally everything you're going to do from this point forward.
It is the foundation of parametric statistics. When you run an independent samples t-test, an analysis of variance in ANOVA, or a multiple linear regression, the underlying math relies heavily on the assumption that sampling distributions are normally distributed.
When you clean your dataset, load it into your software, and eagerly click Run, the computer is doing precisely what we just did in our mental simulation.
Right.
It is checking where your specific hard-won sample landed on that theoretical bell curve of random chance. When you understand the architecture of that curve, you stop being a passive user of a black box algorithm.
You become a scientist who actually understands the geometry of their own logic.
You gain the ability to interpret your results not just as a binary significant or not significant, but as a highly nuanced measure of effect and error. You understand the vulnerability of your data.
Exactly.
Let's do a high-level distillation of the cognitive journey we just mapped out. We started in the abstract and visible realm of the population distribution, the vast ocean of absolute truth that we can never fully measure, defined by theoretical parameters.
We then move to the concrete reality of the sample distribution, the single imperfect bucket of water that represents the actual data we managed to collect, defined by observable statistics and plagued by sampling error.
And we bridged those two vastly different worlds by constructing the sampling distribution of the mean. By conceptually running our experiment thousands of times and plotting the averages, we uncovered the central limit theorem.
The mathematical law that promises us that no matter how chaotic, skewed, or flat the underlying population might be, if our sample size is sufficiently large, the distribution of averages will relentlessly form a predictable, symmetrical bell curve.
And finally, we demonstrated how that very specific bell curve, defined by its standard error acts as the ultimate lie detector test for scientific research.
It defines the strict boundaries of random chance.
Right, allowing us to confidently identify when a psychological intervention has actually changed the trajectory of human behavior.
It is a remarkably elegant system for extracting signal from noise.
Before we wrap up, I want to leave you with a final, slightly provocative thought to ponder, which builds upon a fascinating observation tucked away in the source text.
Oh, this is good.
The text briefly notes that many of the psychological constructs we care most about, things like general intelligence, extroversion, or resilience, are not simple single-source traits.
No, they're widely theorized to be the aggregate averages of hundreds, if not thousands, of different specific underlying variables.
That is the consensus in modern psychometrics. Human intelligence is not a single lever in the brain. It is the incredibly complex sum of verbal ability, working memory capacity, spatial processing speed, nutritional factors during early development, genetic predispositions, and countless localized environmental interactions.
So if a complex human trait is essentially just an internal average of a massive number of smaller, independent, random variables interacting with each other.
Now, according to the very laws of the central limit theorem we just discussed, the population distribution of that trait itself should naturally form a normal bell curve.
The implications of that are profound. It suggests that the normal distribution is not just a statistical tool we invented to analyze data.
Right.
It is a fundamental architectural blueprint of biological reality.
Just look around you. Why is the bell curve found literally everywhere in the natural world? Why do heights, blood pressures, birth weights, and complex personality traits all tend to naturally fall into this exact same mathematical shape?
Because nature itself is constantly taking averages. Every complex organism is a result of thousands of tiny, independent genetic and environmental coin flips.
Nature is running the simulation constantly, billions of times a second. The central limit theorem is the reason the bell curve is the definitive signature of the natural world. It is the math that governs biology. That is something heavy to think about the next time you are quietly coding survey data in the lab.
It certainly elevates statistics from a tedious methodology requirement to a lens through which we can perceive the underlying order of the universe.
Thank you so much for taking the time to tackle this genuinely difficult, conceptually dense topic with us today. We know it is a difficult language to learn, but by grappling with the underlying logic instead of just memorizing the formulas, you are well on your way to becoming fiercely fluent.
May your standard errors be small and your insights be profound.
And remember, the next time you look at a confusing data set, when human behavior seems entirely chaotic, unpredictable, and resistant to being understood, just trust in the math. With a large enough sample, the noise cancels out, the fog clears, and the bell curve always shines through.